All right, I'm going to talk about some types of energy that's going to be used in this particular unit. Right off the bat, if you look at the top, I've listed a bunch of different types of energies that we're going to cover throughout the course of this unit. But the ones that are circled are the ones that I'm going to talk about, and the ones that are actually used in this particular unit, these will be used throughout the rest of the year. So up here I've got kinetic, this is gravitational potential, elastic potential, and then we have other things that again we're going to get to later on in the year: thermal energy, chemical energy, nuclear energy, and electrical energy. But again, for the most part today, I'm going to focus on these ones, these three. Okay, so talking about kinetic energy, most likely you've heard the term kinetic energy before. We've already talked about kinematics, which is always associated with things that are in motion. Same thing with kinetic energy. It actually stems from a Greek word that does mean motion. I'm not going to try to pronounce that. Probably kinetikos, so I guess I am going to try to pronounce it. But there's a pretty simple equation for kinetic energy. First of all, the object must have mass and it must have a velocity. So right here we've got 1/2 mv squared. That is equal to the kinetic energy of the object. Now, this is the AP version of the kinetic energy equation. IB version just says EK is 1/2 mv squared. It's the same equation, they just use slightly different symbols for it. I have also seen KE. Don't let it make a difference for you. They all stand for the same darn thing. They all have 1/2 mv squared. Okay. Another one that is fairly easy to figure out is gravitational potential energy. It says objects at heights can do work when they fall. Now that can be a bit confusing, but when you have an object at a certain height and you allow it to fall, it can do work by changing the form of energy. As an example, if I just drop a book, as it falls, its speed increases. Therefore, you're taking potential energy and you're converting it into kinetic energy. You're doing work. You are changing the type of energy that is present. So, again, it's a pretty simple formula. Kinetic energy is equal to mgh. Okay. In AP, they like to use delta UG. This is like the change in it, which I also think there needs to be like a delta in there for H, but whatever. And then with IB, they like to use delta EP for potential energy, and it's mg delta H. So I do like that delta H in there, because most of the time, if we're going to change something's potential energy, we're going to change its height. We're rarely going to change its mass, and I guess we'll rarely change its gravitational constant too. So again, you've got UG, you've got EP, and again, I've also seen PE. Again, they're all the same thing. Okay, so don't let it mess with you. All right. One that's going to be requires a bit more background, okay, is elastic potential energy, which is caused by something stretching or compressing. It's kind of a way of actually storing energy so that you can use it later. But it really stems from a graphical origin. So if I have a graph of force versus displacement, so if I'm going to start stretching a spring and I want to find out what happens to the force as I stretch the spring, okay, what I end up with is a real nice linear relationship between force and displacement. Okay, so force would be equal to the slope, whatever that slope is, and if you look at the units, we'd have newtons per meter, okay, times the displacement. Okay, now that particular number, that numerical value, is known as a spring constant, and it gets the letter K. And if you look at it, what exactly is a spring constant? It's newtons per meter, a force per unit of distance. Okay, for example, if you had something that said 50 for a spring constant, well, that means it would require 50 newtons to stretch it a meter. Okay, or if you had 5 newtons to stretch it a meter. So the larger the number, the tougher the spring. Okay, if you have the little spring that's in your pens, those are really easy to stretch. They would have a very low spring constant. But the shocks or struts on your vehicle would have a very large spring constant, because it requires quite a bit of force to stretch those things. Okay, now this particular relationship, F equals sum or K times delta X, this is known as Hooke's law. Let me get this in there. Okay, so F is negative K delta X. In AP, they like to put the negative sign in there because the force is always opposite of the direction that you're stretching it. And if you think about it, that makes sense, because if I pull down on a spring, when I let go, it snaps back up. It snaps opposite of the direction that I pulled it. I don't think it's that necessary to think of that all the time, but it will be shown on your equation sheet. IB, it's not on your equation sheet, but you should be aware of it. But IB just likes to say F is KS, S instead of delta X for displacement. Okay. Something else that I've done on here is I've shaded in this particular area. Okay, because we've known from other graphs that area can oftentimes tell us some important things. Well, this is a triangle, so if I look at the area, it's 1/2 base times height. Okay, so if I look at that, well, 1/2, okay, well, the base is delta X, and the height is F, so I've got F times the displacement. Okay, that's pretty much the same thing as work. Okay, it's a Newton meter, which is a joule. Okay, so that's actually the work being done on the spring. The area of a force versus displacement graph is the work done on the spring. Okay, so all right. So if the area of a force versus displacement graph is the work, we could also think of that as a change in energy. Well, what is that energy? Okay, well, if we look at this particular formula again, work being 1/2 F parallel to delta X, if I go ahead and I substitute in Hooke's law for that, I would get work is 1/2 negative K X times X, or 1/2 K delta X squared, or X squared. Now I got rid of the negative just because I don't think it's important to have it in there. Okay, so it says, since we are doing work on the spring, we are increasing its elastic potential energy. As I stretch the spring, it has the ability to spring back and give something energy. I always like to think of dart guns. If you pull back on the trigger, it stretches the spring or compresses the spring to a certain point, and then you release it and it shoots a little dart out. It has the ability to take potential energy and create kinetic energy with the dart. Okay, so since work is the same thing as a change in energy, we can write an equation. We can basically just substitute work for a type of energy. In this case, it's elastic potential energy. Okay, so AP likes to use US, 1/2 KX squared. IB likes to use elas. Don't ask why. 1/2 KS squared. Okay, so those are the types of energies that we're going to be looking at during this unit.